Hi, welcome to the Linux channel. So one of the things you study when you study about operating systems or process or tasks in an operating system, so that it facilitates end applications to be executed on that operating system platform. So operating system is nothing but a software platform to facilitate multiple applications to run on top of it. So as a part of that, you must have studied the Linux has a sort of arrangement where user space applications can run on top of the kernel space, and the kernel manages these tasks or processes, and you may have multiple processes, and each process sometimes can have multi-threaded processes and stuff like that. So one of the things is, when you do study about these in the college, they make a huge fuss about it, and they make it so look complicated. So let me just make it simplified. And also, as I shoot most of my episodes, this is still not a video I'm taking in a context like a really somebody like a fresher. So this is somebody who is in the industry at the same time, who also wants to learn the ground up basics in a kind of in a different way. And also sometimes this can also be helpful for architects in terms of when they are designing the system and stuff like that. So when you compile a code, you get a binary of the same. When you compile a simple GCC application, you get the binary of the same, and then what you do is you execute the binary, and then the Linux kernel will execute the same, and just it does whatever it is mentioned in the code, and then it spits out the output. So essentially this is nothing like just we are handovering a piece of instructions to the OS kernel, and the kernel is facilitating, and it is executing on demand, and it does that as per the way it should be scheduled and stuff like that. So let's just make this as simple as possible to understand. Let's assume this is a specific code. It has multiple instructions, and then once the process is registered in the kernel, you get a data structure to register the process and various other things happening in the background. So once it gets registered, once it gets into that executable context, it just executes the same. But since it is a time sharing, or else it does multi tasking in the same mission. So what happens is, it does execution to an extent, and after that it just hops on to another process, and then it executes that process again. After that, it does that in multiple times, so that each time it hops on to one process after another process. Let's assume it's just a single core CPU based system, so it just hops on to each process, and then let's ignore the priority of the process and all other various stuff. Of course you can do various things, and then you can arrange whichever way you want. So let's just ignore all those things. Just let's assume a piece of code or software like this, or your executable binary. So as it executes, it just hops on to another binary, and it executes from wherever it has left, and then like that it does the same. And then after some point of time, it hops on to the same code again, and then it executes from wherever it has left. Since it is doing this hop again and again, it has to maintain a record, so that it should understand where it has to continue execution of the same, and then again to which extent it has to do the same. So in case if something is high priority and something is interrupting this particular process execution, it is going to do the context switching, and then it is going to hop once again, and then it's going to do the same. So if the system is really slow, you can see that most of these applications, whatever you kept it open, it can be a smartphone or it can be any system. So you can see that the overall sluggishness of the performance, and if the system is good configuration, you can see that smooth execution. The reason is, most of these modern operating systems are multi-process operating system. So as it runs many processes all together at once, it does this time sharing. It does that sharing of that execution space. The execution space is anytime, or execution context is anytime this process is actually being executed onto the CPU, so that it's consuming that CPU resource. So that's what it is. So let's take example like this. like you have two pieces of paper representing one process and another process. So as it does, let's assume this process is started first, and then after some time this process is started first. Let's assume this is like a huge code, and as it gets executed, after that, as I said, it just hops on to another process and it executes the same. So to an extent it executes, and then again it hops on to this, again it executes, again it hops on, and again it executes. So that way it does that scheduling. So this is what exactly is process scheduling or task scheduling in an operating system. So again, this is not something like hugely to be complicated, and not necessary to kind of think that it is really cumbersome to understand. It's very simple in a way, if you can understand as simple as possible. But if you see the Linux code, you should understand the Linux code is so mature. It's a very modern operating system. Although it is a couple of decades old, it is very much evolving, and so you will have a ton of features in terms of doing the same. You can do various strategies, you can prioritize, you can also do preemption based on the device type. Let's assume it's a desktop device, let's assume it's a server device or a real-time system. So based on that, it does various things. So you get that more and more jargon, and you get more and more things to learn about the same. So in a way, it is still easy to understand. So so now let's assume the memory associated with this specific process. So this is one of the things I don't like using the word memory at all. So this is something often I tell to my students, I don't like the word memory at all. So try to become not always a software engineer, try to be somebody who is a end user of your system as well. So think about it. If you are buying a computer, you buy the CPU, you buy the motherboard, you buy the RAM and other stuff. So let's call physical memory, whenever you say physical memory, that this is something programmers do, and all this textbook jargon uses this word. So when you use physical memory, just stop using the word physical memory, just say RAM. It is just physical memory is nothing but RAM. And sometimes, of course, with swap memory, it is going to be even your hard disk. So let's think about RAM. So if you think the kernel itself, the kernel itself runs directly on the physical memory or the RAM. So it doesn't do any virtualization, virtual memory and other stuff, because you don't need to. So because the kernel itself is the base software, I mean to say the operating system, when I say kernel is operating system, it itself is the base software which should facilitate a sort of platform to run your application space processes on top of it. So when a kernel gets booted up and it occupies the hardware, the system resources first, and then it also holds that physical memory or your main RAM, and then it allocates whatever space it needs, and then it just leaves the rest of the memory vacant. So here is where the context, anytime you create a process, again I'm saying you, this is something the operating system is facilitating to make user applications to run on that specific system. So what happens is it creates this process execution context, and then along with that it creates that virtual memory. You should understand virtual memory just like a sort of scrapbook, like I just use sometimes a clipboard like this to write some rough stuff. Anybody calls me or anything to be written, I just write it, and then again I throw whichever pages I have written and stuff like this. Sometimes any important stuff I mark it down to my another large clipboard, and otherwise it is just used as a quick rough book as such. So that's what essentially happens. So as it creates the process execution context, it creates also a sort of a scrap space like this, and then like a rough book, so that it can immediately like maintain its memory aspects. Whenever you create a variable, whenever you allocate any memory resources like malloc and other stuff, and as well as your static variables and other stuff, what it happens is it creates this memory space, illusionary memory space. That is what we call it as virtual memory. Since it is in the it's a illusionary memory space, it has to be somewhere mapped onto the physical RAM, so physical memory, or your actual RAM. So that is why you get that concepts like paging and other stuff, whereas it has to map this huge virtual memory onto a small physical memory space. So you should understand the operating system itself doesn't use this virtual memory space, because why it has already the physical memory space, it doesn't need to. So this is what it is. So don't get confused. Whenever you create a process, you get that virtual memory space, huge virtual memory space. You can just keep doing malloc and allocate so much virtual memory space than actual RAM what you have in the system. So this is what it is. So the thing is, it is just a virtual memory space, and assume the RAM is very small. It's just going to use your available swap space, and that's why you again provide some length of swap space. And if you have an SSD, the swap space will be mounted on your SSD hard drive, and swap space will be much faster. And if you are having an hard disk drive, the swap space will be mounted on a hard disk drive, and it is going to be slower. So this is what essentially happens. So that is what is the reason when you create a process, it creates this illusionary virtual memory space, and then what happens is it is also going to be available exclusive for this process. So essentially what is that it means, if you do some goof up in your code, and if your code is crashing, it is not going to crash the entire system. So this is the important thing in a system like Linux versus systems like which uses a microkernel or hybrid kernel architecture, something like Windows, because there essentially certain kernel components are being put in the user space. So it is not strictly a sort of monolithic sort of arrangement like Linux. So this is where certain things what you study in the college about this process and the operating system concepts, you cannot just apply on real world use cases or real world examples like Linux and something like Windows or something else as well. So you should understand what is the type of the operating system, and then you need to think how far it is going to be applicable. Something you learned in the college is not essentially going to happen in the real world. So you should understand, in the case like Linux, they often refer, whenever the operating system books, they often refer systems like Unix systems. If you are reading very old books, and if you are reading some modern books, and if it is an updated revision or something like that, they may often refer Linux kernel or something like that. So that in that case what happens is you get this virtual memory, and if you do any goof up, again I am reverting back to the topic, so if you do any goof up in the software, it is going to crash the process or your application, but it is not going to create any sort of issues in the system, because everything is happening in this virtual space, and it is also going to not affect the system. So essentially it is going to die, and it is going to create segmentation fault or whatever it is. So if you if you are familiar with crashing applications in Linux system, whereas in the case of kernel, if something happens in the kernel, the entire system will die, because kernel is the main facilitator to provide the system resources in terms of your software offering of a system. So you should understand kernel is nothing but it's a facilitator of your using your hardware resources through the software platform. So this is what it is. And one more interesting thing is you should understand, anytime you have a process and then you have this virtual memory space, assume you have created main of, and in that code you have like int a, b, c, and some global variables you have assigned. So now let's assume you have this virtual memory space, and let's assume you have another process without an IPC. Assume if this process is able to access the virtual memory space of this process. Now what is the thing is, this is what we call a sort of security hole or security breach, and this can happen in case if there is some kind of virus or some kind of system security lapse. So in this case what is happening is there is some kind of leakage in the system where kernel is having some kind of a bug, and it is able to leak that information of this virtual memory space to this another process which is not belong to this virtual memory space. So let's associate this is your virtual memory space, and this is your this is your virtual memory space, this is your process context where it is associated. But let's assume you have another rogue process and it is trying to control this virtual memory space, it is trying to corrupt this memory or trying to read its contents, and it can have any variables containing passwords and stuff like that. So if it manages to do so, and then it is a sort of system vulnerability, and this can happen in case if kernel is having any kind of bugs or some kind of security holes, or somebody have inserted some kind of kernel module or something like that, some kind of system breach. So this is what it is. So this should never happen in an ideal system, and if it happens, you should imagine that there is some kind of security hole, and you should understand this is the reason you need to have IPC mechanisms like message queues and sockets and other stuff to communicate from one process to other process, which essentially means you have this virtual memory space of this process, it should able to communicate a virtual memory space of this another process. So you should have a proper IPC. Again, this IPC is managed by kernel, because the kernel is the system facilitator. The operating system is nothing but it's a facilitator. It is what provides you the platform. So this is what it is. So if you are boarding an aircraft, you have there are different people in the aircraft. Some are the some of the guys are the crew of the aircraft, so they are working for that company, and whereas you are just a passenger. A passenger should always carry a ticket and then boarding pass, and then they need to board the flight and take that journey. Whereas if you think about the employees of that airliner, they don't need the boarding pass. They may have some ID card and other airport verification systems, and then they can just work over there. So this is what it is. So you should understand that's the job of an operating system. It's a facilitator. What is an application process is just a client of that operating system. Whereas if you compile the specific code as per that operating system, it is going to be an a binary meant for that operating system. This is the reason you need to have a compiled code for Linux. You cannot have this compiled code executable directly onto a Windows system. You need some sort of application so that it interprets this and able to run. In the case like Wine, you can imagine you can run Windows executables on a Linux system. Wine is a sort of intermediate platform, so that it takes these Windows applications and it can able to convert that, and it can able to execute on a Linux like system. So this is what it is. So directly you cannot do one application compiled for one operating system as it is. You take it and then execute in another operating system. This is not something again possible. And at the same time, if you have one application compiled for one operating system of a specific hardware, you cannot again take this application just like that and then run it on another operating system or same operating system compiled for another hardware. So you may have a GCC compiled code meant for x86 64-bit. You cannot take this code and then run on some sort of ARM based board with x86 64-bit to same Linux system. So this is where again you need this cross compilation and other stuff, because essentially your compiled code is platform specific. It is having the object level code and other stuff, so it is highly platform specific. You cannot just take this code and just run it on a different hardware platform. So this is what it's an interesting stuff, and once you go through about the process and other stuff, you may find the process execution states. You can find all this pictures whenever you search in the Google. So before I take you guys to the desktop, I would like to also show, generally I maintain this large clipboard, and this large clipboard I write generally various tasks. Some are like high priority, some are like quick tasks, some are like long term objectives and other stuff. So I have like that so many pages as you can see here. So whenever I finish a task, I generally strike with a red ink pen. Hope this camera captures to an extent. So you can see here, you can get some idea, and I have mentioned here do some study on LXC and other stuff, Linux containers and other stuff. This is one task, but I have not crossed it because it is not yet complete, whereas there are certain other stuff which are complete. So whenever I need to do some work in the website, whenever I need to do some work in the Toffee or even Linux channel, I generally write sometimes in this so that I don't forget, and sometimes I need to do some work after this month end or during this month end, I generally make note of the same. So this is how I maintain the same. If you see in air traffic control, they too have a sort of mechanism like this. So whenever a flight is flight is about to land, they will have some kind of plates so that they know that what is the series and sequence of this flights which are supposed to schedule for landing and other stuff, and they know after what flight the next flight is going to land and going to take off, and they will have a list of those stuff in their table all the time. So in case if there is any emergency landing, they just prioritize and then they just make a note that this is going to land first, the other flights are supposed to land next, and then this will be communicated to the pilot as well via the radio, and things are managed. So this is how an operating system also facilitate in terms of running user space application processes in an operating system platform, like in a case like Linux or any operating system. So this is one of the job of any operating system. So if you Google search, or if you do something like operating system OS process states, you get pictures like this. Yeah, you get pictures like this, and you can also find in a case like Linux what can be the process states. We can search directly as Linux process states, and you can find here various pictures depicting overall the entire idea of the same. You have the stopped, executing, ready, and other states. So we can trace this code in the Linux kernel. So if you go here, I am inside the file include linux schedule.h, and inside this file you have this data structure task struct, and this is the data structure which is having this process states. So if you see here, one of the member variables of this data structure is this state, and if you go little up, you can see various hash defines over here. Yeah, you can see here hash define, task running, task interruptible, and other stuff, whatever you've seen in that picture. So if you want to check any examples of this implementation, you can just search this word over here, and you can see there are various places it has been referenced, and you can click any such example. So let's take this. So you can see here in this case there is an example struct, task struct, and this is the instance passed. I mean, this is the argument passed for that API, get wchan, something like that. So if you see here, you have this p which is nothing but instance of or pointer to that task struct data structure. So if you see here, p of state is equal to task running, and then they are doing something. And same way you can just go back, and then you can also see task stopped or something like that, interruptible. Let's say task stopped. Yeah. And again you can see here some real examples of the same. You can see here each case they are doing some is something based on each particular situation as such. So this is what you can study in the textbook. So in my next episode, what I'm going to do is I'm going to cover in depth about the struct, task struct, data structure as well. And I'm going to give some more examples so that we can understand more clearly. So to wrap up this episode, it's very simple. The operating system is the facilitator to run the applications on top of the operating system. However, this is so interesting. If you have a microkernel architecture, things are little different. If you have monolithic kernel, things are little different. And whereas if you have something like Android, it is completely different, because Android is a unique operating system. As a whole, it runs on top of Linux kernel, so it's an OS on top of another OS, and that is the reason when you have Android applications, these are not Linux applications, although Android runs on top of Linux. So you should understand these applications are like sort of like the way you run Java, you have the Java compiled class file, and then this class file should need a JVM interpreter, and then this class files will run on top of a JVM, and JVM runs in a sort of application process context on top of a Linux system or any Windows system. So this is what essentially happens. So if you see a JVM architecture, Java JVM, so let's do an image search. Yeah, something like this. So you can see here, it is interesting. You can see here execution engine, and you have some JVM components, and on top you have this class file. So when you load a Java class file, Java compiled class files, these are not a system object binary file. This is some sort of a object file for the JVM, and JVM will interpret this and runs it inside the JVM, and JVM as a whole loads as a user space application process. So this is what happens. So similar thing happens in case if you run any PHP script, if you run any sort of scripting languages. Take for example HTML pages. So if you see here, these HTML pages, whatever the browser is running is also the same case. You see the browser is a user space application process, and it is running, it is able to interpret that scripting files, it is able to render the images. In this case, it's an image. It is able to take that JPEG file, it is able to take that PNG file, and it is able to render that picture, and it is able to show over here. So in this case, you have this process which is nothing but Mozilla Firefox. Similar way, you have multiple processes. Anytime if you open any of this applications, I'm running Google Chrome. So if you see here, anytime if you run any of these applications, each application is nothing but user space process running on top of Linux kernel, and kernel is what facilitates to happen. So anytime if you need to communicate or share data to and fro from these user space processes, you need an IPC mechanism. And in case if you are able to communicate without any standard IPC mechanisms, assume that system is hacked. So that's about it. So this is what it is. So this is just an intro topic. Subsequently in my other episodes, I'm going to cover more in depth. So hopefully this gives a kind of broader perspective rather than what you generally study in your textbooks so far. So this is what it is. So hope you liked watching this video. In case if you have anything to discuss, be in touch in mail, and in case if you are interested to join classes, go and explore classes page. And some students are confused about this model, since I am kind of created this model really for working professionals, really who are in the industry, even having decades of experience, but they want to learn about certain aspects of the system, and they want to do some R&D of certain things. So go through the FAQ video, and then you can get that better understanding. So in case if you are interested to join the classes as well, you can be in touch in the mail, and we can work about the same. So thank you once again for watching this video. Have a nice day. Take care. Bye bye.